So I'd like to just start off by thanking Maya and all the organizers for inviting me to come back to San Sebastian. This is a lovely, wonderful place. If you haven't been here before, it's going to be a real treat. So this is a course about topological superconductivity. I'm going to start with topological and introduce to you the way that we think about topology in the context of electronic phases of matter. Okay, and so symmetry and topology are two of the big ideas that we have for thinking about matter. So symmetry is sort of familiar and has obvious applications to the phases of crystalline matter. For instance, if you look at these pictures, topology is about something else. So symmetry is about what can you do to a system that keeps it the same. Okay, and so topology is about what is it that stays the same if you make a continuous deformation. And so the classic example of this is the sense in which a coffee cup is the same as a donut. Okay, and so I want to introduce you to the idea that we can use topology to distinguish phases of matter. Okay, in the same way that one can use, so symmetry is also a way of distinguishing phases of matter as well. And so, the way that topology sort of enters into quantum mechanics is through the principle of adiabatic continuity. Okay, and so when you have a energy gap. Okay, so if you have a quantum phase that has a ground state that is separated by an energy gap from its excited states, then you can make a smooth deformation of the quantum state, and provided the energy gap remains finite, then there's a sense in which nothing has happened. Okay, and so these continuous deformations define a notion of topological equivalence, kind of the same as the way a coffee cup and a donut are the same. Okay, and but that doesn't mean everything is the same. Okay, and so there can be gapped states that are different, and then they are going to be separated by some kind of critical point where the energy gap has to go to zero. Okay, and so it's an interesting question then to try to understand and classify all of the kinds of gapped quantum states that you can have, and then you could understand all the possible kinds of transitions that you could have between them. Okay, now the problem with that is that that is a really hard problem. Okay, so in general, many particle quantum states are complicated. Okay, and there's a lot of information in a many particle wave function, and extracting the sort of topological possibilities is a very rich but also very difficult problem in general. Okay, and so I'm not going to answer that big problem for you, but what I'm going to do is I'm going to answer a smaller problem, which is to restrict myself at the beginning to phases of matter that can be described using single particle quantum mechanics. Okay, sort of thinking about one electron at a time. Okay, and so these are going to be states that are adiabatically connected to non-interacting electrons. Okay, and if you have non-interacting electrons, then you can solve the single particle band structure. There's a band structure of silicon. Right, has an energy gap. And now, that doesn't mean that there aren't any interactions in silicon. It's just the interactions, you can imagine just sort of turning them off adiabatically, and they don't change the ground state. You stay in the same topological class. Okay, and so this is the subject of topological band theories. That's what I'm going to spend most of this morning's lecture talking about, which is how we apply topology to the band theory of solids. And so what we have is we have a Hamiltonian, which is now going to be defined as a function of momentum. It's defined in the Brodmann zone. Okay, and so it's an interesting quantum mechanics problem when you have a Hamiltonian which is a function of a set of parameters. Okay, and so that introduces topology into the problem. Okay, and so there are many applications of this. Okay, and let me just say, so there are many examples of topological band phenomena. Claudia is gonna talk about, how these come to life in the real world. Okay, but states that are adiabatically connected to independent electrons. There's the quantum Hall, the integer quantum Hall states, Chern insulators, topological insulators, and then there's a whole. Once one includes different kinds of symmetries, then there's a whole. Lots and lots of different kinds of things. Now, superconductivity, of course, is an intrinsically interacting problem, but it can be described using mean field theory, the BCS model of superconductivity, and in that sense, it sort of fits in the same framework of topological band theory. One has to expand the notion of band theory to include Bogolubov-de Gennes Hamiltonians. Okay, but once you do that, then it's the same kind of problem of topologically classifying band structures. Okay. So these are the sort of single particle states. Now there's a whole big frontier beyond that. I'm not going to say too much about this in these lectures, and I think some of the other speakers are going to sort of take off on this, and so this is of course a huge frontier of theoretical physics to understand these things. Okay, so let's start off with, so this is what I'm going to do today. So I'm going to talk about band topology in one dimension, band topology in two dimensions, and then various generalizations. Okay, and then in the lecture tomorrow, I'm going to talk about superconductivity and how symmetries can sort of enrich the topological classes. But I'm going to spend a fair amount of time just talking about topology without symmetry. Okay. So the sort of starting point for topological band theory is just the band theory of solids, where using Bloch's theorem, then what we know is if you have translation symmetry, you have a lattice translation symmetry, you have a set of operators that commute with the Hamiltonian, so you can classify eigenstates by their eigenvalues, and that defines the crystal momentum, which lives in a Brillouin zone, okay, which is a sort of periodic. It's a torus in two dimensions. Okay, that defines the Bloch Hamiltonian, which is parameterized by k, and so one has a set of a Hamiltonian, which is a function of k. One has a set of eigenvectors and a set of eigenvalues. Okay, and so that's what a band structure is. Okay, so it's a Hamiltonian, or equivalently a set of eigenvalues and eigenvectors which are parameterized by the momentum. Okay, and so when you have a Hamiltonian which is parameterized by a set of parameters, then there's an interesting thing, which is that in quantum mechanics, nobody tells you what the phase of the wave function is. Okay, the phase is there's an intrinsic ambiguity about what the phase of the wave function is. Okay, and that ambiguity, when you have a Hamiltonian which is a function of parameter, then that leads to something very interesting, because you're allowed to choose that phase differently for different values of k. You can change your mind. Okay, and so what that introduces is the idea of the Berry phase. Okay, and so the thing is that I can do a gauge transformation which changes the phase as a function of k, and that gauge transformation is just like an electromagnetic gauge transformation. The only difference is that in electromagnetism you do a gauge transformation as a function of position, whereas here we're doing it in momentum space. Okay, and so if you do that, then there's a natural quantity one can define, which is like the vector potential. When you do a gauge transformation in electromagnetism, you change the vector potential, and so given the Bloch wave functions, one can define this quantity, which is called the connection. Okay, and it has the property that if you change your mind about the phase, then it transforms in the same way that the vector potential transforms under a gauge transformation. Okay, and now of course since this is an arbitrary phase, it can't impact anything physical that you could measure. Okay, just like the vector potential, you can't measure the vector potential. You can only measure things that are gauge invariant. And so you can't measure the phase of the wave function, but what you can do is you can measure the change in the phase when you go through a closed loop. Or you can measure the difference of two phases when you do an interference. Okay? And so the change in the phase when you go through a closed loop is then going to be a loop integral of the vector potential, and that's just like the magnetic flux in electromagnetism. Okay, and so one can define the analog of the magnetic field, the curl of the vector potential, and this is called it's called the Berry curvature. Okay, and of course the Berry phase is around a loop is the integral of the Berry curvature, using Stokes' theorem. Okay, so the Berry phase plays a very foundational role in thinking about topological band theory, and there is one example that everybody has to know about for the Berry phase, and this is the most important example in all of quantum mechanics, which is the two-level system. Okay, and so if you have a two-level Hamiltonian, your Hamiltonian's a 2x2 matrix. And aside from a constant piece, which is trivial, that 2x2 matrix is just like a spin in a magnetic field. Okay, and so I can describe it by a vector D dotted into the Pauli matrix. Okay, and so you learn quantum mechanics, you know what the eigenstates of a spin are. They're just a spinner pointing in that direction, and the eigenvalue is going to be the magnitude of D, and then and you could write down the wave function. The important thing to know is that if you have a closed loop in parameter space, so this vector D traces out some direction on the unit sphere, then the famous result, and if you haven't been through this calculation, this is a quantum mechanics homework problem. The famous result is that the Berry phase, when you go around a closed loop, is equal to 1/2 of the solid angle that you sweep out. Okay, and so that's worth knowing. And in particular, if you rotate by 360 degrees, then the solid angle is half the sphere, which is 2 pi. So the Berry phase is pi. Okay, and so that's the minus sign that you pick up when you rotate a spin by 2 pi. Okay, you can think about that as a Berry phase. Okay, so this is the Berry phase. So now you could ask the question. Okay, so Berry phase is this sort of abstract concept. How does it relate to something physical in the context of the band theory of solids? Okay, and so there the connection of the Berry phase to something physical is through the electric polarization. And so let me just remind you what electric polarization is. So go back and remember your beginning E and M. If you have a polarization is a dipole moment per unit length. So you imagine you have a bunch of polar, molecules, and the charge is related to the polarization. The bound charge is the divergence of the polarization. And then if you have a polarization at the end, there will be a surface charge. Okay? So the interesting question is if you have a band structure, what's the polarization? Okay? And it's not a completely trivial problem, because when you do band theory, what you always do is it with periodic boundary conditions. That's how you calculate a band structure as a function of K. You assume translation symmetry, which means you have periodic boundary conditions. And so you don't have a boundary in order to evaluate the surface charge on. Okay, and so the question is, how do you compute the electric polarization in a band structure? Okay, and so and the answer to that is that it's the Berry phase. Okay, and so you see, the problem is that your block states you can't calculate the dipole moment in a block state because it's extended. It goes off. So you can only calculate the dipole moment if you have a state that is localized, where you can localize where the charge is. And so the way you can analyze this, though, is you can, given if you have, let's suppose you have a filled valence band, okay? Out of the states in the valence band, you can construct localized states. So of course, each K state is extended, but I can make a superposition of them that's localized. Okay, and so it's sort of like doing a Fourier transform. You can define Wannier states, which are basically the Fourier transform of the block band states. Okay, and these Wannier states can be defined, associated with any, of course, it's a Fourier series, right? Because the Brillouin zone is periodic. Okay, and so the Fourier components are going to be defined at discrete lattice vectors. Okay, and so you have a set of Wannier states that are localized on some lattice site, and then once you define those Wannier states, then you can calculate the polarization. You can calculate the expectation value of the position relative to its sort of home base here. Okay, so you can calculate this, and so this is another calculation that is worthwhile to do at some point in your life, like now, which is to do this calculation, and with a couple of steps of algebra, you can turn that into the integral of the Berry phase. It's just a matter of plugging the definition into this. Okay, and so that's a satisfying calculation to do. Okay, and so the upshot of this is that if you compute, so in one dimension you have a one-dimensional Brillouin zone, which is basically a circle, it goes from minus pi to pi. Okay, and so you can calculate the Berry phase going around that circle, and that Berry phase is the electric polarization. Okay, now so there's a very nice connection here. Now there's some subtlety of this, which makes it more interesting than you might first think. Okay, because I told you that the vector potential is not gauge invariant. Okay, so you can't measure the vector potential. Now, of course, the loop integral of the vector potential, is gauge invariant, at least for a small gauge transformation that's continuously related to the identity. Okay, but there are large gauge transformations that change this. Okay, and so there's an intrinsic ambiguity in the electric polarization. Okay, and this ambiguity makes complete sense. Okay, so let's, rather than talking about the Berry phase, let's talk about the polarization. So in one dimension, I can think of the polarization as being the charge at the end. Okay, but what's the charge at the end? Is this some intrinsic property of the bulk, the inside? Okay, and it isn't, because I could always just add another electron to the end. Okay, or I could add 2 electrons. So, but I can't add half an electron. Okay, so if the polarization is 1/2, then you can't get rid of that 1/2. Okay, so intrinsically, the electric polarization is only defined modulo the electric charge. Okay, because you can always add electrons. Okay, so the end charge is really only defined mod E, and this is precisely the ambiguity of the Berry phase. Okay, so the Berry phase, if I do a gauge transformation, where I modify the phase of the wave function with a k-dependent phase in such a way that this gauge transformation, the phase winds by 2 pi when I go around the Brillouin zone, okay, then that will change this Berry phase by an integer. Okay, and that's precisely corresponds to the ambiguity of the polarization. So it's no accident that, the connection between the Berry phase and the polarization, it has to have this intrinsic ambiguity to it. Okay, and this is going to lead to more interesting things when we step up the dimension one higher. Okay, so the polarization is not intrinsically defined by itself because it's only defined mod e. But one thing that is defined completely is the change in the polarization if you tune some parameter. Okay, because actually one other point I'll make about there's something special about this loop that I'm taking when I go around the Brillouin zone. And this loop is a special loop in the sense that it's not the boundary of an interior. Okay, so I can't use Stokes' theorem to write the loop integral of A in terms of the integral of the curvature of the magnetic field. Okay, and so that but if I do the change in the polarization, then I have two loop integrals going around the Brillouin zone, and they are the boundary of an inside. And so then I can use Stokes' theorem to write that in terms of this intrinsically gauge invariant Berry curvature. Okay, and so so this is an important thing, which is that if I'm talking about the change in the Berry phase, the change in the Berry phase is completely defined, whereas the Berry phase going around a closed loop by itself is only defined up to an integer. Okay. All right. So given this, what I'd like to do is I'd like to show you these sort of abstract ideas at work in the context of a simple model. And in one dimension, there's a very simple model that's worth knowing, which is called the Su-Schrieffer-Heeger model. And so what it is it's just a simple tight binding model, one-dimensional tight binding model with alternating hopping. Okay, and so I have strong bonds and weak bonds, and the thing that's kind of interesting about this, is, and if I have, so if the bonds are the same, then if you have a half-filled band, it'll be a metal, and if the bonds are different, then it's just like the nearly free electron gas. You open up a gap at the zone boundary, and so you have an insulator. And the thing that's interesting about this insulator is there are two different kinds, right? You can either go, strong, weak, or you can go weak, strong, and those are both insulators. But I'm going to argue to you that they're topologically distinct insulators. Okay, so we can, so you can write down. So the way you analyze this is, you write down the tight binding model in real space, and then you define. You write it down in momentum space. So you just Fourier transform to write it in terms of CK, and then that defines so there are two sites per unit cell, and so your block Hamiltonian is going to be a 2x2 matrix, and you can read off that 2x2 matrix from this basically. There's going to be a sigma x, a sigma y. There's no sigma z. Okay. And so this is what the 2x2 matrix looks like. And so once we write it like this, then we can ask the question, what's the Berry phase going around the Brillouin zone? Okay, and so there are two possibilities, depending on the sign of this dimerization. So if the dimerization is positive, then what you can see is that this term is bigger than this one, which means that dx never gets to 0. And so if I think about how this d vector evolves as I go around the Brillouin zone, it's just going like this. Okay, so it's not going around the origin, so it doesn't sweep out any solid angle. Whereas if delta t is negative, then this term is bigger than this one, so that means dx is going to be both positive and negative, and so in that case, it goes all the way around, okay? And so that gives the Berry phase of pi. Okay, and so these two states, these two insulating states of the Symmetry-Heeger model are distinguished by their Berry phase, and they're distinguished by their polarization. And it makes complete sense because you know, these two pictures are exactly related to if you just slide over by half a unit cell. Okay, so so there's a polar, you know, this has a polarization of 0, you know, relative to the center of a bond, and this has a polarization of E over 2. Okay, now, so I want to say that you know, these two insulating states are topologically different. Okay, you know, obviously I can't get from delta t positive to delta t negative without going through delta t equals 0. And if delta t equals 0, then the gap closes, and that's this quantum phase transition. But of course, and it makes sense that there are two kinds of, you know, loops in the plane. Either they go around the origin or they don't, or actually they could go around the origin any number of times. So there should be an integer winding number. But who's to say that dz is equal to 0? So obviously in this model, dz is equal to 0. But there's nothing wrong with having a sigma z term in the Hamiltonian. Okay? And in general, there could be one. I could write down a term in this that would give me a sigma z. And then that would make the loop come out of the plane, and so the Berry phase would no longer be quantized, and it wouldn't be topological anymore. Okay? And so when you talk about topological states in one dimension, you need something more than just topology. You need some symmetry. Okay? And so actually it's useful to think about what the symmetries of the Symmetry-Heeger model are. There are two different kinds. The first one I'll call a chiral symmetry, and it's a kind of funny kind of symmetry. Usually symmetries are described by operators that commute with the Hamiltonian. This chiral symmetry is an operator that anti-commutes with the Hamiltonian. Okay? And obviously, if your Hamiltonian only involves sigma x and sigma y, then it anti-commutes with sigma z. Okay? And so if that's the case, which it is the case for the Symmetry-Heeger model, okay, then that leads to something very interesting, because what it means is that if you have an eigenstate at positive energy, then if I apply sigma z to it, then I'm going to get an eigenstate with exactly the same negative energy. Okay? So having this chiral symmetry means that eigenstates come in pairs, okay, at positive energy and negative energy. So the spectrum is sort of reflection symmetric about E equals 0. Okay, so it has particle hole symmetry. Okay, you know, and if we have this chiral symmetry, then you know dz has to be equal to 0. I mean, you know, if you had a sigma z, then you wouldn't have the chiral symmetry. And so there's going to be an integer winding number you can have, okay? And so there's going to be an integer topological invariant that characterizes this polarization. Now, of course, this is a model symmetry. It's not a physical symmetry of real polyacetylene. Okay, real polyacetylene will have second neighbor hopping. You know, the spectrum won't be particle hole symmetric. There's no physical principle that makes the spectrum of a band structure particle hole symmetric. Okay, at least not until we get to superconductivity. Okay, so this is an artificial symmetry. Okay, but nonetheless, it's very useful to understand the consequences of this symmetry, because it gives you a point where you can understand things. Okay, and so just because it's not a real physical symmetry doesn't mean we shouldn't think about it. But there is a real symmetry that polyacetylene has, which is a reflection symmetry. Okay, so if you take x to minus x, if you reflect about the center of a bond, then you do have that symmetry, and that symmetry is constrains the Hamiltonian in a slightly different way. Okay, so this is an operator that commutes with the Hamiltonian. Okay, and it takes k to minus k, of course. So, and now, so one can ask what the what the consequence of this symmetry is, and it gives a constraint on the d vector. So it's not, it doesn't force dz to be equal to 0. So you could have dz equals 0. You'll have dz if you have, again, second neighbor hopping. If I include that in the Symmetry-for-Higger model. Okay, and there's no reason for that to be equal to 0. So, but it does give this constraint. So d of k and d of minus k are going to be related to each other, and so that's enough to protect the topological classes. So it turns out that that in this case, if you have the reflection symmetry, then there are only going to be two classes. There's not going to be an integer topological invariant. It's a Z2 topological invariant, and that a Z2 topological invariant is basically whether the polarization is 0 or E over 2, mod E. Right? The polarization is only defined mod E, so it can either be 0 or E over 2. So that's the Z2 topological invariant. Okay. All right, so this is the Symmetry-for-Higger model. So the bottom line here is that there's no topology in one dimension. Okay? So in one dimension, you need some symmetry in order to get some topological classes. Okay? But let's step it up to 2 dimensions. Actually, before I do that, let's suppose we have this symmetry. Let's suppose, what consequence does it have? And this is the sort of most important consequence in topological band theory, which is that when you have boundaries between topologically distinct insulators, then you get topological boundary modes. And again, the SSH model is the simplest place where you can see this at work. Okay, and all you have to do is draw the picture. You can see that if you have a domain wall between these two phases, then there's going to be an atom that gets left behind in the middle. Okay, and that atom is going to have a 0 mode. So the simplest thing to consider is when the weak bonds are equal to 0 and the strong bonds are big. Okay, because then you just have a bunch of decoupled dimers. Okay, and each dimer is going to split into a sort of bonding and anti-bonding state. Okay, and then this one in the middle is going to be left behind. It's going to be at 0. So you get a 0 mode now. So of course you can ask, well, what happens to that 0 mode if now I turn up the weak bonds again? Okay, and so this is a situation where the chiral symmetry is very useful to think about. So let's suppose we have the chiral symmetry. So then what we know is that the spectrum has to be particle hole symmetric. Okay, so every state at positive energy has a partner at negative energy. Okay, but this 0 mode is its own partner. Right? There's nothing wrong with that. Okay, but you see, the thing is, if it's its own partner, then you can't get rid of it. Okay, so when I turn up the weak bonds, nothing can happen to that 0 mode, because in order to move away from 0, its partner would have to appear out of nowhere, and that can't happen. That can't happen continuously. Okay, and so you can immediately understand why this 0 mode is topologically protected, and it'll be a 0 mode even if you turn up the weak bonds so that they're almost equal to the strong bonds. So, and in that limit, you have a very small gap, but you're still going to have a 0 mode inside the gap. Okay, and so this is a phenomenon that was sort of discovered and rediscovered many times. Actually, I think I'm telling it backwards. It was first discovered by the field theorists. So a useful limit to consider in this SSH model is the limit where the strong and the weak bonds are almost equal to each other. Then you have a very small gap, and so you can do a theory which is just describing the low energy degrees of freedom near the conduction and valence band. And that theory has the form of a one-dimensional Dirac Hamiltonian. Okay, and so that looks like this. Okay, and this model, again, it has this chiral symmetry. So sigma z anti-commutes with the Hamiltonian. It only involves sigma x and sigma y. And so it has this particle hole symmetric spectrum. And so Jakiv and Rebbe were the ones who realized that had a protected zero mode. Okay? And so here's another homework problem for you. If you have not done this calculation before, then it's a very satisfying calculation to do, which is to show that for this Hamiltonian, this eigenstate is an exact, this state is an exact zero energy eigenstate of that Hamiltonian. Okay, it's simple. All you have to do is plug this into the time-independent Schrodinger equation. And the right-hand side of the time-independent Schrodinger equation is equal to 0, because E is equal to 0. Okay, and so this is an exact zero mode no matter what m of x is, as long as m of x changes sign. Okay, and so if m changes sign, then this is an exact zero. Okay, so that's a homework problem for you. So okay, now so we have these zero modes, and so there's one more point. So this SSH model is very simple, but it has lots of deep things in it. And so one thing that it allows us to think about clearly is there are sort of two levels to thinking about topological band theory. Okay? There is the single particle level, and there's the many-body level. Okay, so the single particle level, we're talking about a one-body, Schrodinger equation, which has a band structure, h of k, so it's the single particle quantum mechanics. We're just talking about one particle. And that has this zero energy eigenstate, okay, and that's the consequence of that. But, when we're talking about electrons, there are lots of electrons. They fill up the valence band. And so you have a many-body ground state of the filled valence band. Okay? And so then the interesting thing is that, this zero mode can either be occupied or not occupied by an electron. And due to this particle hole symmetric spectrum, what we expect is that those two states should have opposite charge. Okay? But they differ in charge by 1. And so that means that those two states have charge E over 2. Okay? And it kind of makes sense because I told you the polarization of the B state was E over 2, so then that's the divergence of P. The divergence of the polarization is E over 2. Okay? But just ponder this for a moment. Something amazing has happened. Okay? Electric charge is indivisible. It's quantized in units of E. Okay? You can't have, you can't have a fractional charge. We're not talking about quarks here. Okay? But this E over 2 is sharply quantized. Okay? And it can move around. So it's kind of like a fractionally charged particle. And this is part of the essence of charge fractionalization. Okay? And so what you can think of, you can imagine you start in the A phase and you add an electron. Then you can nucleate a B phase and you can split that electron in half. Okay? And so one of the ways of thinking about topological band theory is to think about all of the kinds of ways you can split the indivisible. Okay, things that you can't split up in apart by inserting a topological phase, you can split them. Okay, and so let me give you another example of that, stepping up a dimension here, which is, so let's talk about a one-dimensional metal. Okay, and so, this could be undimerized polyacetylene. Okay, so it has energy as a function of K filled up to the Fermi energy. And the states near the Fermi energy are going to be states which are moving to the right or moving to the left. Okay, the problem with one-dimensional conductors is they're very fragile, right? Because if you make them a little bit dirty, they become localized. Or if you add a weak periodic potential, then that's commensurate with the number of electrons, then you open up an energy gap. Okay, and so and turn it into an insulator. Okay, so what I want to show you is that the right moving and left moving electrons, they're on top of each other. Okay, you can't so you can't have just the right movers by themselves in a one-dimensional system. Okay, but I want to show you can split them, and the way they split is it's kind of just like the SSH model. Okay, so let's start with a trivial insulator, which is just a bunch of these one-dimensional wires with weak periodic potential. Okay. Then what I'm going to do, what I'm going to do is instead of coupling the right movers on the same wire, I'm going to couple the right movers to the left movers on the neighboring wires. Okay, and so if you do that in the middle here, I'm going to open up a gap by coupling the right movers on one wire to the left movers on the next wire. Okay, and if you do that, then there's going to be an energy gap, and I'm going to argue to you that this defines a Chern insulator. Okay, but on the boundary between these two insulators, there's a right mover that is left behind. It's kind of just like what happened in the SSH model. Okay, and so if you could do this, then you would have a right-moving electron by itself. Okay, and that would be a wonderful thing to have. Okay, and so let me just tell you how wonderful this right-moving electron would be. So it's one way, right? And that means you put in an electron, with 100% certainty it's going to come out the other side. There's nowhere else for it to go. Okay, and again, one can think about this on two levels. There's the single particle level, and there's the many body level. Okay, so on the single particle, on the single particle level, we have insulators on either side. So there's a conduction band and a valence band separated by an energy gap. But then, on this boundary, there's going to be a band of states which connects the conduction band and the valence band, which has, a positive group velocity, positive slope. And, there's no way you can get rid of that. Okay, if you imagine trying to continuously change this band structure, there's no way you can get rid of this chiral mode. Okay, so it's a topologically protected feature of the single particle spectrum. Okay, so that's the single particle point of view. But so the many body picture is that you have these single particle states that are filled up to the Fermi energy, and that defines a many body ground state. And the many body low energy excitations, which are going to be the little particle hole excitations, about this Fermi energy. Okay, and so this defines what I will call a chiral Fermi liquid. Okay, and it can be described in terms of a low energy theory that describes the excitations near this Fermi point. And this has the structure of a conformal field theory, basically. This chiral Fermi liquid has fundamental properties, which it has a quantized electrical conductance, where if you raise the chemical potential of these edge states a little bit, then a current, an excess current will flow. And the ratio of the current to the voltage is E squared over H. Okay? And it also has a quantized thermal conductance, okay, where if I raise the temperature of the edge a little bit, then an excess thermal current will flow. And that defines another topologically quantized quantity, which we call C, which is called the chiral central charge. Okay? And so these are two distinct sort of topological properties of this many-body ground state of a chiral Fermi liquid. Okay? The quantized electrical conductance is also related to something called the chiral anomaly, which is related to the fact that if you just have this chiral Fermi liquid, just the right mover by itself, then the electric charge, if in the presence of an electric field, the electric charge of a chiral fermion is not conserved. Okay, and I mean, if you understand the quantum Hall effect, this is a trivial consequence, because if you apply a electric field, then there's going to be a charge flowing from the bulk. And so basically, if I apply an electric field, then as a function of time, the dk dt, there's a force, so dk dt is non-zero, and that gives rise to a change in the charge density. Okay, and so the chiral anomaly is something which is very simple to understand in this context. Okay, right. So this says that there should be some topological structure that one could define in 2 dimensions, and so and this is what the quantum Hall effect is about. Okay, and of course it was the quantum Hall effect that was the whole genesis of this set of ideas. Sort of grew out of the discoveries in the quantum Hall effect. And let me just say, so this is what happens if you have a 2-dimensional electron gas in a magnetic field. You get Landau levels, and when you have filled Landau levels, you get a quantized Hall conductance. And let me just say one thing. Of course, this was back in the 1980s that these experiments measuring the quantized Hall conductance were done, and it's remarkable. You can measure this integer to 1 part in a billion. And in fact, this quantization is now how the ruling authorities in standards and units define the unit of the kilogram is now defined with this experiment. Okay, it's not that rock that was stored in a vault in France anymore. Okay, but this has been around for some time. But one thing I'll say, the quantized thermal conductance, that experiment was really only done in the last 5 years. Okay, so there's still life in this, and so this is an interesting, it's not 1 part in a billion here, but nonetheless. This quantized thermal conductance is a distinct topological property that these systems have. Okay, so what I want to do, and let's see now, do I have an hour or do I stop at 10?
Yeah,
You want me to stop at 10? Okay, so that means I think I have 3 minutes.
5 minutes.
Okay.
Yeah, you can speak 5 more.
Yeah. Okay. Yeah. I don't want to spend more time than I'm invited for. But let me tell you what the Chern number is. I can do this. Okay. So and because we have all of the ingredients that we need, because I told you about the polarization and the intrinsic ambiguity of the polarization. And so if you have a 2-dimensional band structure, okay, then I can define a Berry connection in 2 dimensions, which is like a 2-dimensional vector potential, okay, and so I can define the Berry phase going around a cycle of the 2-dimensional Brillouin zone, And of course, that Berry phase is only defined mod E, just like the polarization. Okay? So it's not topological. The Berry phase by itself is not a topological quantity. But what I can do is I can compare the Berry phase here with the Berry phase here. Okay? Now, on the one hand, since the Brillouin zone is a torus, these two lines are the same line. Okay? So the polarization has to be the same. But on the other hand, the Berry phase, when I calculate the polarization as the line integral of the vector potential, that is only defined mod E. And so these two have to be the same, but they're only defined up to an integer. So they could differ by an integer. Okay? But moreover, since I have the bottom of the Brillouin zone and the top of the Brillouin zone, I could use Stokes' theorem to evaluate it in terms of the Berry curvature on the inside. Okay, and so what we learn from this is that this integral of the Berry curvature doesn't have to be zero. It could be non-zero, but if it's non-zero, it has to be an integer. Okay, and so that's the Chern number. Okay, and the physical meaning of this Chern number, so it's an integer topological invariant. The physical meaning is the Hall conductance, and the way you can think about that is the connection is through the Laughlin's argument for the quantum Hall effect. And so if you make a cylinder out of the quantum Hall effect, okay, and let's suppose that cylinder, I define my unit cell, so there's just one unit cell going around the cylinder. Okay? So then as a function of magnetic flux, that's just like as a function of Ky. So Ky plays exactly the same role as magnetic flux. Okay? And so if I thread a flux quantum and compare the polarization before and after I threaded the flux quantum, that's exactly evaluating the Berry phase here and here. Okay? And if I thread the flux, then Laughlin's argument is if you have a dB dt, then Faraday's law says there's going to be an electric field going around. Okay? And if you have an electric field going around, then if you have a sigma xy, then there will be a Hall current flowing. And so while you're turning up the magnetic field, then there's a Hall current flows. And so if you then integrate up the charge that flows, then you get precisely sigma x. If you insert one flux quantum, h over e of flux, then you get sigma xy times h over e. Okay, and so since this polarization is quantized, then that explains the quantized Hall effect in terms of the Chern number. Okay, and so this is the sort of physical connection between the Chern number and the quantized Hall conductance. Okay, there's another calculation you can do, which is the calculation that Thalles and et al. Did, which is to use the Kubo formula. That's a little bit more complicated version of this calculation. Okay, so I'm done. So we will continue with some of this tomorrow morning. Okay, thank you. Do we have time for questions? Okay, yeah. Please. Yeah.
Thanks for talking. So like this central charge that you showed. Thanks for the talk. So the central charge that you showed.
Yes.
Is this like an SPT invariant? Or
no? There's no symmetry. It's just T.
Oh, but because it's called chiral.
Chiral in the sense that if I have a chiral fermion, right, which is just a right mover. Okay, so it's not because of chiral symmetry. Yeah.
Okay. So it's defined for the 2D system and not for one of the 1D systems that you put together.
Well, it's defined for the one-dimensional boundary. So if I have the one-dimensional boundary of the two-dimensional system, I can have a chiral fermion. This edge state is a one-dimensional chiral fermion, which is by itself not mathematically well defined. Okay, and that's what the chiral anomaly is about, and the chiral central charge is something that characterizes that as well. Yeah.
Okay, so then it's more like not of the Fermi liquid, but then of the 1D, like the Luttinger liquid, I guess, like a property.
Chiral
right?
Luttinger liquid.
Okay.
Yeah.
Okay.
Yeah.
I see. Thanks.
Yes.
You said that large gauge transformation is equivalent to any charge. Said the large gauge
Yes,
transformation.
that's right. Yeah.
But that's a different physical state, right? Does gauge transformation?
Well, no. Let me put it this way: the large gauge. So if I do the large gauge transformation, what that is like doing is that's like moving everything over by one space. Okay, and so if I move all the electrons over by one space, then there's going to be one extra electron at the end. So then I could remove that electron, and I get back to where I started. Okay.
Okay. Thanks.
Yeah.
Hi, thanks a lot for the lecture. I wanted also to ask about the chiral Fermi liquid, because as far as I know, in the conventional Fermi liquid, you justify all this temperature dependence and so on by saying that these low energy excitations, because of Pauli's principle, and this is also something you can derive with the Fermi-Gordon rule, cannot decay, and this is how you get the square dependence with the energy. But how can you get the same dependencies as you are getting here with something so different as the concept of being topological protecting this current state?
Well,
this energy?
I mean, I would say that, so certainly for free fermions, you can understand the low energy spectrum of the free fermions, just by thinking about the electron states. But one can also understand that same low energy spectrum in the context of like conformal field theory. Okay, and that is a more general way of describing the same thing. Okay, and so it's not that I wouldn't say it's different. It's just an alternative description of the same thing, which allows generalizations. Okay, and so what it allows, for instance, is it allows one to consider interacting systems. Okay, and the structure of even in the interacting ground state, the structure of the low energy, excitations stays the same. Okay, as it did, there's some things that stay the same as the non-interacting case. Okay, but the conformal field theory allows a way of describing that the low energy excitations even in the interacting system.
Okay, so the excitations are the same, but you get for free also the cutoffs.
I get what?
The cutoffs also with conformal field theory, so you get two for the price of one.
I'm sorry, I couldn't understand.
That if you are mapping this Fermi liquid theory to something like lattice and so on, you also get more easier description because you also get lattice parameters and so on. I mean, like these theories that usually diverge, ultraviolet and infrared divergences, I mean.
Right, yeah, okay.
Nice, thanks.
All right, thank you.